Hi guys, and welcome to this virtual lecture course on Quantum Condensed Matter Physics. I'm Dr. Andrew Mitchell, and in this lecture we'll be discussing the theory of Green's functions in the context of quantum many-body systems. Many of you may know Green's functions from other areas of mathematics or physics, where they're very handy in solving differential equations. In the context of quantum many-body physics, the differential equation we'll be solving using these Green's functions is, of course, the Schrödinger equation. We'll see, however, that Green's functions in condensed matter physics have a very nice and intuitive interpretation as a single particle propagator. It tells us what is the probability that if I put a particle into the system at a particular point, at a particular time, then I can take it out of the system somewhere else at a different time. It tells us about the dynamics of the system, how the electrons are moving through the system, and what their correlations are in time. We'll be discussing this theory, which is a very rich and powerful theory. It's really one of the workhorses of quantum condensed matter physics. In this lecture, we'll start from basics. We're going to write down the definitions of these Green's functions, and we'll see how we can formulate them in terms of the time domain or the frequency domain, and also in terms of a complex variable z. We will see the physical interpretations of these Green's functions and how to actually just go ahead and calculate them for a given simple system. The system we'll start with is the simplest possible system of a time-independent single quantum orbital with a particular level energy, and we'll derive all of the Green's functions for this system. We'll talk about how the retarded Green's functions are related to the density of states of the system. We'll also talk about the fluctuation-dissipation theorem and how the Green's functions are related to orbital occupation. We'll then have a look at a time-dependent Hamiltonian, and we'll go through the same process again for this non-equilibrium situation. We'll look at the situation of a so-called quantum quench, where we suddenly change the Hamiltonian at t equals 0 and see how the dynamics of the system evolves. Finally, we'll have an outlook towards systems with many quantum orbitals, which is of course what we want to look at in this course. In the coming lectures, we'll return to this, and we'll be developing further the theory of Green's functions, but the foundational material will be contained in this lecture. So let's get down to work.
In this lecture, we'll be discussing Green's functions in the context of quantum condensed matter physics. But before we get into that, let me give some of the mathematical background behind the theory of Green's functions. Suppose that we have a linear differential operator L hat, which is a function of the coordinate x. Let's say that we then wish to solve differential equations of the type L hat acting on u of x is equal to f of x. So here we have on the right-hand side a source term, f of x, and the linear differential operator L hat on the left-hand side, and we want to solve this equation for this function u of x, which u of x, when operated on by L hat, gives us the source term f of x. One way of solving differential equations of this type is to use Green's functions. We construct a Green's function g, which is a function of x and s, such that when L hat acts upon the Green's function, we get the delta function, the Dirac delta function, delta of x minus s. By multiplying both sides of this equation by f of s, and then integrating over s, we then easily obtain a solution to u of x. So if we know the Green's function, g of x and s, we can easily find solutions to differential equations of this type. Some of you may have already encountered Green's functions in the context of classical physics. In particular, it's widely used in the theory of electrodynamics. For example, let's take the Poisson equation, where we have a differential operator which is the Laplacian, del squared, acting upon our electrostatic potential phi of r, and this is equal on the right-hand side to minus 1 upon epsilon naught times the charge density rho of r. In analogy to the above expression involving our Lx operator, our solution u of x, and our source term f of x, here we see that the differential operator L hat is the Laplacian del squared. The source term here is basically the charge density rho of r, and the solution that we're after is the electrostatic potential phi of r. We can now introduce a Green's function g, which is a function of two coordinates r and r primed. In a translationally invariant system, however, we can express this in terms of a single variable, r minus r primed. We define our Green's function g of r such that when we operate on it with our Laplacian, we get the delta distribution delta of r. Substituting this into the Poisson equation, we then find an expression for our electrical potential. The reason why this construction is useful is that the defining equation for the Green's function here, that Laplacian acting on the Green's function gives the delta function, is a much easier equation to solve than the generic Poisson equation, where the right-hand side has some complicated source term. In particular, we can solve the Green's function equation here, in this case by means of a simple Fourier transformation. If we go to k-space, then we find very straightforwardly that g of k is just equal to minus 1 upon k squared, and I'll leave that as an exercise for you. Going back to real space, we can then substitute our expression for g of r into the equation for the electrical potential. This then immediately gives us the well-known expression for the potential created by an arbitrary charge distribution. Okay, so how can we use this Green's function theory in the context of quantum condensed matter physics? Of course, in quantum condensed matter physics, the differential equation that we're interested in solving is the Schrödinger equation, h psi is equal to e psi, or likewise the time-dependent Schrödinger equation, I d by dt of psi is equal to h psi. For a single particle Hamiltonian, we can then simply define a corresponding Green's function which solves the Schrödinger equation. We can write that E minus h acting on the Green's function is equal to the delta function. Here I've allowed the Green's function to have arguments r and r primed, but on the right-hand side we see that this is equal to the delta function of r minus r primed. So in fact, r and r primed must enter in the Green's function only in the combination r minus r primed. In the position representation, the Green's function is therefore diagonal, and we only have a single collective variable r minus r primed. We can then naturally identify the inverse Green's function, g inverse of a variable r, as being simply e minus h of r. This then implies that g inverse of r multiplied by g of r minus r primed is equal to the delta function r minus r primed, as desired. This is nice because it provides an alternative way of writing the Schrödinger equation. G inverse acting on the wave function psi is equal to 0. We can now play exactly the same game with the time-dependent Schrödinger equation, which I've written again here. We introduce a Green's function g, which now depends on the position r and the time t, as well as r primed and t primed. On the right-hand side, we therefore have Dirac delta distributions for position, delta of r minus r primed, as well as time, delta of t minus t primed. The same logic applies. On the right-hand side, we see that we have a function only of r minus r primed and t minus t primed, so we can define the inverse Green's function just as a function of those two collective variables. G inverse of r and t is therefore equal to I d by dt minus h of r. From these equations, it immediately follows that the wave function psi of r and t can be expressed as the integral over all space of the Green's function multiplied by the wave function of r primed and t primed. This can be very simply verified by taking this expression for the wave function r and t and plugging it in the Schrödinger equation here, and then using the property that this object in square brackets multiplied by this Green's function is equal to these delta functions. This expression therefore tells us that the Green's function can be understood as a single particle propagator. It relates the wave functions at time t primed to a wave function at time t. And as we can see here from the integral, this involves taking the particle at time t primed at all possible positions r primed and propagating it forwards in time to the specific position r. This is rather reminiscent of the Feynman path integral version of quantum mechanics, in which we imagine that the propagation of a particle from time t primed to t involves taking all possible routes from the start point to the end point. So in quantum mechanics, where the Green's functions refer to solutions of the Schrödinger equation, the Green's functions have a physical interpretation as the probability amplitude of taking a particle from position r primed at time t primed and ending up at position r at time t. If we now define the wave function at position r and at time t as the projection of the wave function psi of t onto the position vector r, and given that we know the solution to the time-dependent Schrödinger equation for a single particle, which is written here, psi of t primed, acted on by the time evolution operator e to the minus I h of t minus t primed, propagates the wave function forward to psi of t, then we can simply write the following, where here I've simply taken this equation and now pre-multiplied by bra r, and then interpreted these brackets in terms of psi of r and t on the left-hand side and psi of r and t primed on the right-hand side. I can now insert a complete set of states inside this expression by simply multiplying by the identity operator 1 hat. By resolving the identity operator as an integral over position, we then obtain the following. The wave function psi of r and t is therefore equal to an integral over dr primed of psi of r primed and t primed multiplied by this matrix element that connects r to r primed under the time evolution operator. But using our Green's function formulation, we have a very similar kind of equation. Comparing these two allows us to get an explicit expression, in this case, for the Green's function. We can write that the Green's function g as a function r and t and r primed and t primed is equal to minus I theta of t minus t primed times this matrix element. This theta function here simply tells us that the time t must be greater than the time t primed. That is the order of the events of the propagation that we defined in these equations. Theta of t minus t primed here is simply the Heaviside step function. We start with a wave function at time t primed, and then we imagine propagating forward in time to psi of t. This defines the so-called retarded Green's function, where t is greater than t primed. Sometimes you will see this denoted with the superscript r in the Green's function to emphasize that this is the retarded Green's function. A different but somewhat equivalent solution to the differential equations are the so-called advanced Green's functions, where here we have plus I theta of t primed minus t. And these advanced Green's functions are often denoted by the superscript a. In this case, we assume that the wave function on the left-hand side here, psi of r and t, occurs at a time before the wave function psi of r primed and t primed. We can express these in the following way in terms of these brackets. We see, therefore, that the Green's function is basically associated to the probability amplitude of finding a particle in a state r and t, given that it started at r primed and t primed. The retarded Green's function is the one where t is greater than t primed, and the advanced Green's function is the one where t primed is greater than t. So for the retarded function, we start off in the state r primed and t primed, and we move forward in time to r and t, whereas for the advanced Green's functions, we start in the state r and t and moves forward in time to r primed and t primed. Now I want to emphasize here that so far we've been considering the dynamics of a system with a single particle. However, in condensed matter physics, we're usually interested in systems of many particles. In fact, in the thermodynamic limit, we'd have a very large number of particles, 10 to the 23 or so. So we need to be able to generalize this theory of Green's functions to systems involving many quantum particles. For the remainder of this lecture, and also in the coming lectures, we'll now focus on the single particle Green's functions, but for many particle systems. In many particle physics, we will adopt the same Green's function philosophy that we discussed on the previous slides, but we will need to generalize some of the concepts. Green's functions will describe the dynamics of electrons in many-body quantum systems, not on the individual level of single electrons, but on the statistical level of expectation values. we will see that these Green's functions are really the workhorse of many-body quantum mechanics, and they're very, very powerful indeed. We will see that single-particle Green's functions only contain part of the full information contained in the wave function. However, the information that they do contain tells us a lot about the system, and in fact are closely related to various experimental observables of interest. It turns out that there are various different types of single-particle Green's functions, but the one we'll consider in this lecture course will be the retarded single-particle Green's functions for fermions. I will define it GAB of T and T primed. T and T primed here are the time labels, and A and B are the orbital or site labels. We're going to propagate an electron from site B to site A. To emphasize that this is the retarded Green's function, one can add this superscript r here. However, often I will just drop this and assume that whenever you see a Green's function like this, I'll be talking about the retarded Green's function, unless otherwise stated. The retarded Green's function is defined on the right-hand side here. It's minus I theta of t minus t primed. This, of course, means that t has to be greater than t primed, multiplied by the thermal expectation value of some operators. The operators inside here are the anti-commutator of Ca and Cb dagger, evaluated at time t and t primed respectively. This might seem like a rather complicated and abstract object, but we'll be discussing the physical implications of this in the coming slides. Writing out this anti-commutator here, I see that we have the sum of two terms. The first involves the thermal expectation value of Ca, evaluated at time t, and Cb dagger, evaluated at t primed, whereas the second expectation value has the order of these operators switched. We have Cb dagger evaluated at time t primed, and Ca evaluated at time t. And of course in quantum mechanics, the order of these operators matters, even more so here because they have different time labels. We will denote each of these two terms as so-called Keldysh Green's functions. We call the first term G greater, and the second one minus G lesser. These are denoted by the greater than sign or the less than sign in the superscript here. Specifically, these Keldysh Green's functions are defined as G greater is minus I times the thermal expectation value of Ca of t times Cb dagger of Ct primed, whereas G lesser is plus I times the thermal expectation value of Cb dagger evaluated at time t primed times Ca of t. Notice that in these definitions we don't see the time ordering. There is no theta function. That is pulled outside of the bracket here in the definition of the retarded Green's function. Apart from this decorative factor of minus I and plus I here, we can easily see what these Green's functions mean. The physical interpretation of this G greater is the probability that if I put an electron into the many-particle system at position or orbital B at time t primed, then I can take the electron out at position or orbital A at time t. Notice that this does not have to be the same electron. This is simply the overall thermal expectation value for such a process. Likewise, for the G lesser function, it's the probability that I can take out an electron at orbital A at time t and put one in orbital B at time t primed. And again, here there is no time ordering. T can be after t primed, or t can be before t primed. The order of t and t primed is not specified in these Keldysh Green's functions. Let's now take a look at the special case of systems with time translation invariance. This means that we have a steady state situation. The Hamiltonian does not have a time dependence. Obviously, this is a special case, but it's rather a common case, and it's something that we're going to be studying a lot in this lecture course. Of course, one can have a non-equilibrium steady state, but more commonly, we'll be discussing systems at thermal equilibrium. This means that the thermal expectation value of some operator evaluated at time t is static. It doesn't depend on the time at which you evaluate the expectation value. However, it's a little more subtle when we're talking about the Green's functions because we have two time variables. This tells us that the Green's function GAB of times t and t primed must depend only on the time difference between t and t primed. So from now on, in this case, we'll write GAB of t minus t primed. This is because the Green's function corresponds to a correlation function involving operators acting at times t and t primed. Because of the property of time translation invariance in the system, I can slide t and t primed simultaneously backwards and forwards in time and still get the same answer. However, the correlation will depend on the time difference between t and t primed. There will very naturally be a difference in the correlation between events separated by a short amount of time and events separated by a large amount of time. Indeed, since we can slide t and t primed backwards and forwards in time and still get the same answer, why don't we simply choose t primed to be equal to 0? This then gives us that the Green's function GAB is a function simply of the time t. In terms of the fundamental definition of our retarded Green's function, we can then write that GAB of time t is equal to minus I theta of t times the thermal expectation value of the anticommutator of CA evaluated at time t and CB dagger evaluated at time 0. And just recall here that theta of t is the Heaviside step function, which is equal to 1 when t is greater than or equal to 0, but theta of t is equal to 0 when t is less than 0. Also note that we can write CB dagger evaluated at time 0 simply as CB dagger. We can drop the time label if t is equal to 0. That was all for the retarded Green's function, but we can similarly define the Keldysh components in the same way, where we set t primed explicitly to 0 in our time translation invariant system. In most of what follows, we're going to be considering these equilibrium situations where the Hamiltonian has no explicit time dependence. The system will then have a natural time translational invariance, and the corresponding Green's functions will be functions of a single time variable. You should just bear in mind that this time variable t corresponds to the difference in time for the action of our two operators in the Green's function. Later on in this lecture, however, I will do one example of a system with an explicit time dependence, where the Green's functions then depend on two time variables. But for now, let's just stick with the simplest case. In this case, we can naturally look at the Green's functions not in the time domain, but in the frequency domain. There are actually some subtleties here due to whether we take the Fourier transform or the Laplace transform, and subtleties to do with the convergence of integrals. Let's define the Laplace transformation of the Keldysh Green's function as GAB of the complex variable z is equal to the integral dt from 0 to infinity of e to the I zt of the Green's function GAB as a function of time. I've written this one down explicitly for g greater, but this exact same equation also holds for the g lesser. Here, the complex variable z is defined as omega plus I delta, where omega and delta are pure real, and delta in particular is greater than 0 by definition. This is needed to ensure the convergence of these integrals, as we'll see shortly. The Laplace transformation of the retarded Green's function GAB of t is very similar. Since the retarded GAB of t is equal to theta of t, g greater of t minus g lesser of t, when we do the Laplace transformation, this theta of t doesn't matter because we're already going from 0 to infinity anyway. The time is always positive within this Laplace transformation. Therefore, we can simply write that the retarded GAB of z is equal to g greater of z minus g lesser of z. Everything here is a function of the complex variable z is equal to omega plus I delta. So how does this relate to Green's functions in the frequency domain, which would be obtained by doing a Fourier transform? Well, the Fourier transform is defined as the integral dt from minus infinity to plus infinity of e to the I omega t times the Green's function GAB in the time domain g of t. This would give the Green's function in the frequency domain GAB of omega. However, the definition of the Green's function in the time domain GAB of t, as defined in this equation, has in the definition of it this theta function, theta of t. So when we insert that into this expression, it will of course kill half of this integral, and we'll end up only with the integral dt from 0 to plus infinity. This means that the Green's function in the frequency domain, GAB of omega, is very closely related to that which we obtained by the Laplace transformation, GAB of z. GAB of z, of course, is a function of the complex variable omega plus I delta, with delta defined as being positive. Therefore, we can make the connection between GAB of omega and GAB of z by simply taking the limit of the latter as delta goes to 0. However, since delta is defined as being positive, we have to take this limit of delta goes to 0 plus. That means that delta remains positive, but it can become infinitesimal. In the end, we obtain the Fourier transform of the Green's function in the frequency domain. This might seem rather convoluted and unnecessary. However, we'll see explicitly shortly that we cannot simply do a regular Fourier transform of these Green's functions because the integrals don't converge. We actually need to include an infinitesimal positive imaginary part for these Laplace transformations to be well defined. We can then define the Fourier transform by simply taking the limit of the imaginary part of z to 0 while keeping it infinitesimally positive. This is an example of so-called analytic continuation. We define g in terms of the complex variable z with the positive imaginary part. G is therefore defined everywhere in the upper half complex plane. But then, we examine the behaviour of the Green's function g as we approach the real axis and send delta to 0 while keeping it positive. We therefore obtain g of omega, which is a function of real frequency omega. Let's now have a look at an explicit example. In fact, let's take a look at the simplest possible example of a single, non-interacting, and time-independent quantum orbital. The Hamiltonian h hat reads simply epsilon c dagger c, where epsilon here is the level energy for the single orbital. In the occupation number basis, we have eigenstates 0 and 1, corresponding to the situation with no electrons or a single electron in our quantum orbital, and of course these satisfy the Schrödinger equation h psi equals e psi. Specifically, h acting on the 0 state gives us an eigenvalue of 0 times the 0 state back again, whereas h acting on the 1 state gives us epsilon times the 1 state back again. So the energies are simply 0 if it's unoccupied, and epsilon if it's occupied. Epsilon can therefore be understood as the single particle energy, or local potential energy, for this quantum orbital. Notice here that the Hamiltonian does not have an explicit time dependence, therefore our Green's functions will only involve relative time differences. Let's take a look at the lesser Green's function, g lesser of t. This is defined, as before, as plus I times the thermal expectation value of the c dagger operator acting at time 0 and the c operator acting at time t. So how do we compute such an expectation value? Well, here let's recall that the time evolution of an operator a hat in the Heisenberg picture is given by a hat of t is equal to e to the iht times a times e to the minus iht. And here a hat is the time-independent version of the operator for a time-independent Hamiltonian h hat. We can therefore write that the g lesser Green's function is plus I times the expectation value of a time-independent operator c dagger times e to the iht times a time-independent operator c times e to the minus iht. Next, we need to calculate this thermal expectation value. Now, we should recall that the thermal expectation value of some operator a hat within statistical mechanics is given by 1 over z times the sum over eigenstates j times the Boltzmann weights e to the minus beta ej times the matrix element of the operator a sandwiched between the eigenstates psi j. Here we have the Schrödinger equation h psi is equal to e psi. In particular, if I act with the Hamiltonian on an eigenstate psi j, I get the eigenstate back again times the energy ej. This is the energy Ej that is featuring in the Boltzmann weight here in our statistical sum. The factor z is of course the partition function, which is simply the sum over all of these Boltzmann weights. It's basically normalizing this probability distribution. Finally, beta is the so-called inverse temperature. It's just 1 over kBt, with kb the usual Boltzmann constant. So now we have all of the ingredients to simply go ahead and calculate by hand this G-lesser Green's function. So putting all of this together, we have the following. First, we have this factor of I in the original definition, divided by the partition function, which is the sum of the Boltzmann weights. That's e to the minus beta epsilon plus e to the minus beta 0, because we have two eigenenergies, 0 and epsilon. Then we have the sum of two terms for the two eigenstates. Each of these is weighted by its own Boltzmann factor. The first one, involving the occupied state, involves the Boltzmann factor e to the minus beta epsilon. The second one, involving the state 0, involves the Boltzmann factor e to the minus beta 0. The operators inside these matrix elements are the same. It's c dagger, e to the iht, c, and e to the minus iht. We can already make a simplification here, because e to the minus beta 0 is, of course, simply 1. We can also immediately evaluate e to the minus iht acting on the 1 state, or e to the minus iht acting on the 0 state. That's because this exponential operator here involves the Hamiltonian, and we're working in the eigenbasis. The first of these terms gives us e to the minus I epsilon t acting on the 1 state. That's because, of course, the 1 state is an eigenstate of the Hamiltonian, whereas the second one gives us e to the minus I0t, and again this factor is, of course, just 1 in the end. If you're curious about the way that these exponential operators act, and why I'm allowed to simply replace the operation of the Hamiltonian on the eigenstate when it's in the exponent by simply the eigenvalue, you can think about just expanding this exponential as a Taylor series in powers of the Hamiltonian. Anyway, the resulting factor, e to the minus I epsilon t, or e to the minus I0t, these things are of course just pure numbers and commute through the rest of these operators, so I can collect those exponentials together as common factors. Then I obtain this expression. Importantly, we see here that this second term is actually equal to 0, because we have the action of the annihilation operator c acting on the already empty state. So this gives us 0 and kills that whole second term. Likewise, in the first term, we have the annihilation operator c acting on the occupied state, which of course gives us the 0 state. Furthermore, we can then act on this 0 state by the exponential operator e to the iht, and that will give us e to the I0t in this case. E to the I0t is of course just a factor 1. That's a number that can be commuted outside of the matrix element, which gives us overall the c dagger operator acting on the empty state, which of course gives us the occupied state. So in the end, we're looking at the overlap of the 1 state with itself, and that object is simply equal to 1. So overall, the G-lesser Green's function as a function of time is simply I, e to the minus beta epsilon times e to the minus I epsilon t, divided by the partition function 1 plus e to the minus beta epsilon. If I then multiply this expression top and bottom by e to the plus beta epsilon, then I get this slightly simplified form. Furthermore, this can be expressed in terms of the Fermi-Dirac distribution f of epsilon, defined in the usual way as 1 over 1 plus e to the minus beta epsilon. As we know, the Fermi-Dirac distribution controls the thermal occupation of the orbital, and we see it here entering in the G-lesser Green's function. So we see from this explicit expression that the Green's function G-lesser of t is actually something that is periodic in time. That is because of this factor e to the minus I epsilon t. Using Euler's relation to write e to the I theta as cos theta plus I sine theta, we can then express G lesser of t in this way. The imaginary part of G lesser of t as a function of time is therefore simply a cosine. The amplitude of the oscillation is simply the Fermi function, we see it goes between plus f of epsilon to minus f of epsilon, and the time period is 2 pi upon epsilon. We have a periodic structure to the Green's function, and this goes on forever in time. Before we discuss the corresponding Fourier transforms and the Green's functions in frequency domain, let me make a comment on the equal times Green's function. If we consider again now the 2 times Green's function, g lesser of t and t primed, but now we look at equal times, t primed is equal to t, then that would have the explicit expression written on the right-hand side here. Due to time and translation invariance of the system, given our Hamiltonian does not depend on time, we can evaluate this Green's function at any specific time, and we can choose in particular t equals 0. So in time-independent systems, the equal times Green's function is simply equal to the t equals 0 Green's function. We can now go to our explicit expression for g lesser of t and set t equals to 0 to discover that g lesser of 0 is simply equal to I times the Fermi function f of epsilon. We can also see that from the graph here. The imaginary part of g lesser is equal to f of epsilon. However, g lesser of 0 has another interpretation. Plugging t equals 0 into this expression simply gives us the expectation value of c dagger c. This is of course the expectation value of the number operator for our single site. We can write g lesser of 0 therefore simply as I times the expectation value of the occupation of our site. So we see that we get the static expectation value of the operators when we look at the 0 time or equal time Green's function. Furthermore, we recover the expected result. We see here, by equating these two expressions, that the expectation value of the occupation for our site is given by the Fermi function. This is precisely the meaning of the Fermi function. It's the thermal expectation value of the occupation of a quantum orbital. So all of this makes good sense. Okay, so what about the Green's function in the frequency domain? Well, in the time domain, we see that we have an oscillatory function with a well-defined frequency. Because we have a single frequency to the oscillation, we expect in the frequency domain a delta function. So let's see how that works out mathematically. First of all, let's examine the naive Fourier transform. G lesser of omega is equal to the integral dt over all time of e to the I omega t of g lesser of t. By substituting in this explicit expression for the g lesser Green's function in the time domain, we obtain the following. This looks like a rather simple integral. We have I times the Fermi function f of epsilon times the integral dt over all time of the Fourier factor e to the I omega t times this factor coming from the Green's function e to the minus I epsilon t. Of course, we can collect together these two exponentials here as e to the it multiplied by omega minus epsilon. And now we can simply do the integral. We obtain this object, which is then evaluated at t equals minus infinity and t equals plus infinity. And now we have to pause and think a little bit, because there's some problems with this expression. The first giveaway that there's a problem is that downstairs we have omega minus epsilon. What happens when we want to evaluate the Green's function g of omega at the point omega equals epsilon? This would be undefined because we'd have a divide by zero problem. That's the first hint. The second hint that something's wrong is that we have to evaluate this integral at t equals minus infinity and plus infinity. But as we already saw, e to the it omega minus epsilon is an oscillatory function of time. What value do we assign it at t goes to infinity or minus infinity? We could write e to the it omega minus epsilon as cos t omega minus epsilon plus I sine t omega minus epsilon, but what value do we assign this at t equals infinity? It's oscillating between plus and minus 1. Naively, it might appear that this integral is actually undefined. However, we have to be a bit more careful. From the theory of Fourier analysis, you might recognize the integral dt of e to the it omega minus epsilon is actually the definition of the delta function. So we can actually write that g lesser of omega for pure real frequency omega via the Fourier transform is given by 2 pi I Fermi function f of epsilon times the delta function, the Dirac delta, omega minus epsilon. I'll return to this formulation a bit later. However, first, let's look again at the Laplace transformation of g lesser of z. As before, the Laplace transformation for g lesser of z is defined as the integral dt from 0 to plus infinity this time, of e to the izt times g lesser of t. Here, z is a complex variable, omega plus I delta, where both omega and delta are real, and delta is taken to be positive. Well, going through the same steps as before, you obtain a very similar expression, I f of epsilon times e to the it z minus epsilon over I z minus epsilon, evaluated between t equals 0 and infinity. The integral is well behaved and convergent. First of all, let's look downstairs here. Now we have z minus epsilon on the denominator. As long as that we have a finite imaginary part with delta greater than 0 here, this tells us that the denominator can never actually be equal to 0. That's because epsilon is real. So there's no divide by 0 problem in this equation. So let's have a look now at evaluating this definite integral at the two limits t equals 0 and t equals infinity. Okay, so this lower limit here is obviously well behaved because we plug in t equals 0 there, and the top is equal to 1. What about in the case of t goes to infinity? If we substitute explicitly z equals omega plus I delta, then we obtain the following. In particular, notice that the plus I delta factor on the numerator becomes e to the minus delta t. And if delta is positive, as we've assumed here, then this factor will ensure convergence of the integral as t goes to infinity. This e to the minus delta t will exponentially suppress anything in this expression here as t becomes large. As we've already discussed, this first term is oscillatory and is bounded from plus to minus 1, so this e to the minus delta t will certainly suppress those oscillations at large time, giving us a convergent solution to our problem. On the bottom, we see explicitly that even if omega is equal to epsilon, this will not be a divide by 0 problem because we have a finite imaginary part. So overall, the integral converges. We have a well-behaved function. It evaluates to minus f of epsilon over z minus epsilon. Let me come back to the physical interpretation of this expression when we discuss the corresponding retarded Green's functions in the frequency domain. I will also discuss the relationship between the result for the Fourier transform and the result for the Laplace transform. So far, we've been considering the g lesser function. Now let's turn to the corresponding g greater function. G greater of t is defined as being minus I times the thermal expectation value of the operator c of t and c dagger of 0. We can now evaluate explicitly this expression in exactly the same way as we did for the g lesser. Using the previous definitions of the time evolution of the operator c of t, and also using the expression for the expectation value from statistical mechanics, we obtain the following. This is exactly an analogy to the g lesser function that we considered previously. As before, we can immediately make some simplifications. First of all, e to the minus beta 0 is of course 1 in both of these two factors. Also, we have c dagger acting on the occupied state this time, and this is equal to 0. Whereas in the second term, we have c dagger acting on the unoccupied state, which gives us the 1 state. The expression for g greater of t therefore collapses to this. E to the minus iht acting on the occupied state, of course, gives us the factor of e to the minus I epsilon t times the occupied state back again. E to the minus I epsilon t is of course just a number, commutes through these operators, and we can collect it to the front of the expression. We can therefore write e to the minus I epsilon t times c acting on the 1 state. This of course just gives us the empty state. Then we act one more time with e to the plus iht on the empty state, which gives us a factor of 1, and then we simply have the bracket of 0 with itself, which is 1. So collecting all this together, we have that g greater of t is equal to minus I times e to the minus I epsilon t divided by 1 plus e to the minus beta epsilon. As before, we can now multiply top and bottom by e to the plus beta epsilon. And then I again recognise the Fermi function 1 over 1 plus e to the beta epsilon. So in the end, we see a slightly different expression for g greater. We have a minus sign and this extra factor of e to the beta epsilon. In fact, with a bit more manipulation, we can actually eliminate this factor e to the beta epsilon by expressing it in terms of the Fermi function. I will leave it as an exercise for you to prove that the g greater function can be written in this form, as minus I into 1 minus the Fermi function times the factor e to the minus I epsilon t. Now, we can interpret the factor of 1 minus f of epsilon here as being the population of holes. If f of epsilon was equal to the expectation value of the number operator, that would of course give us the occupation of particles. So 1 minus f is then the occupation of the holes. It might seem rather strange to talk about the population of holes, but it's simply a complementary way of counting things. We can either count the number of particles relative to zero occupation, or we can count the number of holes relative to an occupied site. So we see that the g lesser function is basically the Green's functions for the particles, and the g greater Green's function is the Green's function for the holes. The imaginary part of g greater of t, therefore, again has an oscillatory form. This time, the amplitude goes between 1 minus f of epsilon and f minus epsilon minus 1. Of course, we see the same time period of 2 pi over epsilon for the oscillations. Let's now take a look at the Green's function in the frequency domain. As before, we'll actually apply the Laplace transformation and relate g greater of z to g greater of t by integrating over time from 0 to infinity of e to the izt times the time domain g greater of t function. Following exactly the same steps as before, we obtain that g greater of z is equal to 1 minus the Fermi function divided by z minus epsilon. Alternatively, we can perform the regular Fourier transform, and in that case, very similar to the case of g lesser, we obtain minus 2 pi I 1 minus f of epsilon times the delta function omega minus epsilon. These are two equivalent ways of performing the transformation, either to the complex argument z or to the real frequency omega. So let me now summarize. In the time domain, for this simple example of a single non-interacting time-independent quantum orbital, we have g lesser functions and g greater functions. They're related to this factor e to the minus I epsilon t, and we have these Fermi factors f of epsilon entering. In particular, we're now in a position to calculate the retarded Green's function g of t. As we showed earlier, this is simply theta of t, the Heaviside step function, multiplied by g greater minus g lesser. We can now simply substitute in our expressions for g lesser and greater and find out an explicit expression for g retarded. When we do that, we find that g retarded is simply minus I theta of t times e to the minus I epsilon t. The Fermi functions exactly cancel out. This is very interesting because it tells us that g retarded has no temperature dependence. Notice that the temperature dependence in our thermal expectation values entered entirely through these Fermi functions, and they've cancelled out here. G retarded has no temperature dependence for this non-interacting system. So our retarded Green's functions do not depend on the thermal or statistical occupation of our quantum orbital. So what information does it contain? Well, to answer that question, let's have a look again at the frequency domain. In the frequency domain, and here I mean functions of the complex variable z obtained by the Laplace transformation, we have g lesser of z being minus f of epsilon over z minus epsilon, whereas g greater of z is 1 minus f of epsilon over z minus epsilon. The corresponding retarded Green's function in the frequency domain, g of z, is therefore g greater of z minus g lesser of z, as before, which of course gives us, in this case, 1 over z minus epsilon. Again, we see that the Fermi functions cancel out, they drop out, we have no temperature dependence to the retarded Green's function. In particular, we can now also relate the lesser and greater Green's functions to the retarded function. We find that g lesser is equal to minus the Fermi function times g retarded, whereas g greater is equal to 1 minus the Fermi function times g retarded. These are actually related to the so-called fluctuation-dissipation theorem and are quite general. In fact, they really apply very generally in any equilibrium system, as we'll see. G greater and g lesser can of course also be directly related, and we find that g greater of z is equal to minus g lesser of z times the factor e to the beta epsilon. Note here that there's no simple relationship between g retarded as a function of real frequency, omega, obtained by the standard Fourier transformation, and the g lesser and greater functions as a function of real frequency, omega, obtained by their corresponding Fourier transforms. And that is because if we look at the definition of g retarded in the time domain, given here, we see that it contains this extra theta function. So the Fourier transform of g of t is not simply equal to the difference of the Fourier transforms of g greater and g lesser, because of this extra factor theta of t. But we'll see an alternative formulation for that shortly. So let's now focus on the retarded Green's function for this single orbital. We've just derived that g of z is equal to 1 over z minus epsilon, with a complex z equals omega plus I delta and delta positive. We can now look at the real and imaginary parts of g of z, and we find the following expressions. In particular, you'll see from these expressions that g of z is well-behaved and analytic, meaning not singular, everywhere for delta greater than 0, and we say that the delta regularizes these Green's functions. In particular, I can write minus 1 upon pi of the imaginary parts of the Green's function, g of omega plus I delta, in this way. I write it as 1 over pi delta, all divided by 1 plus omega minus epsilon over delta squared. This is the very definition of the Lorentzian function, centered on omega equals epsilon, and of width delta. So let's now plot this function as a function of epsilon for a given delta. For a fairly large delta, we see the Lorentzian has a rather broad width. In fact, it is easy to show from this explicit form that the peak is located exactly at omega equals epsilon, the peak height is 1 over pi delta, and the half width at half maximum of the peak is exactly delta. Therefore, as we go to a smaller delta, we see that the peak gets higher and it gets narrower, but it's still centered on omega equals epsilon. In fact, as delta goes to 0 but remains infinitesimally positive, we'll see that this will turn into a delta peak, meaning that it has infinitesimal width and infinite height. In fact, the Lorentzian is a mathematically well-defined approximation to the Dirac delta distribution. We can see that because the normalization of the Lorentzian, which is the integral d omega from omega is minus infinity to plus infinity, of this object, minus 1 upon pi of the imaginary part of g, is equal precisely to 1, and that's independent of the delta. This means that if I were to integrate this red curve here, I would find an area under that curve of 1. If I integrate the blue curve, I would find an area of 1. And indeed, as I send delta to 0, keeping it infinitesimally positive, of course, I still find that the normalization of that is equal to 1. And that's one of the important properties of the delta distribution. So we see that as we take the limit of delta goes to 0 plus of minus 1 upon pi of the imaginary part of g, we see exactly the delta function of delta omega minus epsilon. This is an important quantity, and we give it a name. We call it the spectral function. The spectral function a of omega is defined as being the limit of delta goes to 0 plus of minus 1 upon pi of the imaginary part of the corresponding retarded Green's function. For a single quantum orbital, we derived that the retarded g of z is equal to 1 over z minus epsilon, which gives a spectral function a of omega is simply the delta function delta of omega minus epsilon. The spectral function a of omega gives the so-called density of states. Now, for the simple case that we've considered involving a single quantum orbital, the spectral function is simply a delta function. This is a very trivial example. We have a single state in the system located at omega equals epsilon. Therefore, when we're looking at a of omega as a function of omega, we have 0 until we hit omega equals epsilon, and then this delta function basically counts a single state for us. Notice that the integral over all omega of a of omega is equal to 1. The total density of states is normalized to 1. The spectral function a of omega can therefore be thought of as being a probability distribution, containing the probability of finding a state of a given energy. For a system of just a single orbital, we have just a delta function located at the energy of that state. We can also reconstruct the retarded Green's function with a knowledge of the spectral function a of omega and the real part of the Green's function. However, given that the retarded Green's function g is an analytic function of the complex variable z, we know that the real and imaginary parts are related through the Kramers-Kronig transformation. Recall here that an analytic function of a complex variable z is one that has a well-defined and convergent Taylor series in powers of z. We can use the Kramers-Kronig relation to obtain the so-called spectral representation of the retarded Green's function g of z for any complex z. We can therefore write g retarded in this fashion purely in terms of the spectral function. As for the real part of g, we can evaluate it simply as 1 over omega minus epsilon, provided that omega is not equal to epsilon. This is referred to as the principal value of 1 over z minus epsilon. In this case, the real part of g looks something like this, with a divergence around epsilon. The infinitesimal imaginary part of the frequency, omega plus I0 plus here, regularizes this function so that there's no real divergence at omega equals epsilon. But for all intents and purposes, when we're not at omega equals epsilon, we simply see a regular function 1 over omega minus epsilon. So this function 1 over z minus epsilon in the limit of delta goes to 0 plus is rather an interesting one. The imaginary part is only finite when omega is equal to epsilon, when we get a delta function, whereas the real part is only finite and regular when omega is not equal to epsilon, in which case we get 1 over omega minus epsilon. From our explicit expressions for the g lesser and g greater obtained by the Laplace transformation of a complex variable z, and then sending the imaginary part to a positive infinitesimal, we can relate the lesser and greater Green's functions to the spectral function a of omega on the right-hand side. Indeed, given that g retarded can be expressed as g greater minus g lesser, I can take the imaginary part of both sides of the equation and simply relate the imaginary part of g retarded to the spectral function. And of course, we recover the definition of the spectral function that minus 1 upon pi of g retarded is a of omega. Previously, I mentioned that it was not so simple to relate g retarded as a function of pure real frequency omega, obtained by the regular Fourier transformation, in terms of the Fourier transforms of g greater and g lesser. However, the spectral function provides a means to connect these objects. The Fourier transform to real frequency omega of g lesser of omega and g greater than omega can now be cast in terms of the spectral function a of omega. We've derived this explicitly here because g lesser of omega and g greater of omega were expressed in terms of the delta function, omega minus epsilon, for a site of energy epsilon, and we also related the spectral function a of omega to the delta function. However, it turns out that these expressions are totally general and apply in all cases. We can prove that by the so-called Lehmann representation, which we'll talk about in a future lecture. These important relations are known as the fluctuation-dissipation theorem. They relate the occupations of a site to the spectral functions. We can see this by writing the orbital occupation, which is the expectation value of the operator n hat, which can also be written, of course, as the thermal expectation value of c dagger c, in terms of our lesser Green's function. We can write it as minus I g lesser evaluated at t equals 0. This is then the equal times lesser Green's function, which gives us the orbital occupation. We can obtain g lesser of t from g lesser of omega using the inverse Fourier transform. We write 1 upon 2 pi times the integral d omega of e to the minus I omega t times g lesser of omega. The 0 time lesser Green's function is therefore simply obtained by setting t equals to 0 on the right-hand side, which then just means that we integrate g lesser of omega over all omega. We can express the orbital occupation, which is the expectation value of n hat, then simply as minus I upon 2 pi integral d omega of g lesser of omega. Substituting our expression for g lesser of omega into this integral in terms of our spectral function then gives us the following. The orbital occupation is given as the integral d omega of the Fermi function f of omega times the spectral function a of omega. And this is an important result. It tells us how the orbital occupation is related to the spectral function. The orbital occupation is something that depends on temperature, of course. The spectral function does not depend on temperature, but we see how temperature enters this equation through the Fermi functions. Just a final comment on this. This formulation involves Green's functions of the real frequency omega, and we were able to do the inverse Fourier transformation here. Of course, we could have used these equations at the top in terms of our complex variable z, but then we would have had to have done the inverse Laplace transformation, which is a bit more cumbersome. Of course, they both give the same answer, but this version involving the inverse Fourier transformation is certainly easier. Finally, we're in a position to show that the retarded Green's function as a function of the real frequency omega, as would be obtained by a regular Fourier transform, can be expressed in terms of the retarded Green's function as a function of the complex variable z, as we take the imaginary part to be a positive infinitesimal. We can also express this in terms of the spectral representation in the following way. There are another class of Green's functions that I've not yet mentioned called the advanced Green's functions, contrary to the retarded Green's functions. However, the only difference in the definition is that on the bottom here we have omega minus I0 plus, rather than omega plus I0 plus for the retarded Green's function. And therefore, since the only difference is the sign of the imaginary part, we can obtain g advanced simply by taking the complex conjugate of g retarded, and this is really the only difference. Sometimes you'll see these advanced Green's functions mentioned in books or papers. However, we won't discuss them further in this course. We'll just focus on the retarded Green's functions, and suffice it to say that if we wanted the advanced functions, we can obtain them simply by this relation. Now I want to do an example of a situation with a time-dependent Hamiltonian. In that case, we have Green's functions that depend explicitly on two time variables. Here I've written the retarded Green's function in terms of its original definition, and one can of course express this in terms of the greater and lesser functions. These greater and lesser functions are written down here for the case where we have t1 and t2 being arbitrary times. So the example that I want to look at is a so-called quantum quench. This is a paradigmatic situation where the total Hamiltonian h of t on the left here has an explicit time dependence. It is, however, a simple example of time dependence because we go from an initial Hamiltonian, which is some static time-independent Hamiltonian hi, to some final static Hamiltonian hf. And then we see these theta functions of minus t and theta of t here. So basically this says the Hamiltonian h of t is equal to hi when time is less than 0, and then it instantaneously changes to hf for t greater than 0. So at t equals 0, we just change from the initial Hamiltonian to the final Hamiltonian, and that's referred to as a quench. Here we'll consider the simplest possible example of this quantum quench, where our initial or final Hamiltonian, this is h hat alpha, where alpha is either I or f for initial or final, is a single quantum orbital, c dagger c, with a level energy, epsilon, that changes depending on whether or not we're in the initial or final state. One can think about this as having a Hamiltonian h of t that has an energy level epsilon of t that depends explicitly on time, and this is multiplied by the number operator for our site. If I were to plot epsilon of t as a function of time, we would see that it takes a constant value, epsilon I, for t less than 0, and then discontinuously changes to epsilon f for times t greater than 0. So this is a very simple example of time dependence of the Hamiltonian, but we'll still see that it has some interesting physics, and we can explore that physics using these time-dependent Green's functions. I should note here that for time t less than 0, we have an equilibrium situation. The Hamiltonian is constant. If we go to the infinitely distant future, t goes to plus infinity, then we'll also have an equilibrium situation where we've relaxed to our new equilibrium with a different epsilon. This is the epsilon f. However, for finite t greater than 0, we'll see some transient dynamics when a system is relaxing from its old equilibrium to its new equilibrium. And it's this transient behaviour that we'd like to understand here. We will see that it's a little more complicated when we discuss the Green's functions of two time variables, t1 and t2, however, because t1 might be before the quench at t less than 0, and t2 might be after the quench at t greater than 0. Or we could have both t1 and t2 less than 0, or both of them greater than 0. These will correspond to physically quite different regimes. So let's just do the calculation and see what we get. So let's now suppose that the initial level energy epsilon I and the final energy epsilon f are both less than 0. This will mean that the occupied state is the ground state of the system at all times, t less than 0 as well as t greater than 0. For simplicity, let's also specialise now to the 0 temperature limit. This means that we'll only have excitations from this unique ground state. This immediately implies that the g greater function is actually equal to 0 for all times. That's because on the right-hand side here, I have a c dagger operator. But if we're only considering excitations from the occupied ground state in the 0 temperature limit, then we will not be able to apply this c dagger operator. Acting with the c dagger operator at any time on this occupied state will annihilate that state. By contrast, if we look at the g lesser function, then the order of the operators is reversed. This means that here on the right-hand side, I have the annihilation operator acting on the occupied state, and this will be finite. Expressing the time-dependent operators in the Heisenberg form, I can now write the lesser Green's function in this way. Here I'm time-evolving the operators using e to the iht and e to the minus iht. However, the Hamiltonian has to be evaluated at the particular time of interest. For example, in this term, we originally had c of time t1, and therefore we need to evaluate the Hamiltonian at that time, t1. As I mentioned earlier, we therefore need to break this down into the different regimes. First, let's look at the case where both t1 and t2 are negative. In this case, h of t is always the initial Hamiltonian, hi, as I've written here inexplicitly now. We can evaluate this string of operators as before, and we simply obtain I e to the epsilon I into t2 minus t1. We see in this case that g lesser is actually a function only of t2 minus t1, the relative difference between t1 and t2. This is the situation we saw previously for the time-independent Green's functions. The reason why we're getting that again here is that both t1 and t2 are negative, and therefore the dynamics of the system is evolving under a static time-independent Hamiltonian hi. Exactly the same logic holds when both t1 and t2 are greater than 0. Here, the system is evolving under the final Hamiltonian hf, which is time-independent. The Green's functions therefore look exactly the same, except we simply replaced epsilon I with epsilon f. The more interesting case arises when t1 and t2 have different signs. For example, let's look at the case when t1 is greater than 0, that's after the quench, and t2 is less than 0, before the quench. Therefore, in the string of operators, this first term, which has evolved at time t1, applies to the final Hamiltonian hf, whereas this operator is evolved under the initial Hamiltonian because we're at time t2, which is less than 0. When we evaluate this, we find that g lesser is I e to the I epsilon I t2 minus epsilon f t1. So let's now discuss the Laplace transformation to the frequency domain of these Green's functions. First of all, we have to take care of the fact that we have two time arguments, t1 and t2. We'll therefore introduce the label t to mean the average time between t1 and t2, and the label tau to indicate the time difference t1 minus t2. With this change of variables, I can write g lesser as a function of t and tau is equal to I e to the minus I epsilon f tau. We now perform the Laplace transformation on the variable tau. This is the time difference between t1 and t2. This will give us a Green's function g lesser, which is something that depends on time, but also on this complex variable z. We want to keep this time argument here because we want to know the Green's functions as a function of the real time in the system. The dynamics of the system in these correlation functions are encoded in the time difference, which is tau, and this is the variable that we're Laplace transforming to the complex variable z. Evaluating this integral explicitly, we obtain minus 1 over z minus epsilon f, and we see on the right-hand side that this Green's function is not depending explicitly on the time labelled t. This is actually as expected because, as we argued right at the beginning, when both t1 and t2 have the same sign, we'll have an equilibrium situation. In this case, with t1 and t2 both greater than 0, the dynamics are controlled by the final Hamiltonian, and therefore we have epsilon f appearing downstairs here. As before, we can now define a retarded Green's function of the complex variable z in terms of g greater minus g lesser. It's just that now we carry this additional time label t. We also argued that at 0 temperature, this g greater function was equal to 0. And therefore, overall, we have that the retarded Green's function is simply 1 over z minus epsilon f. Again, this confirms our original assumption that if both t1 and t2 are positive, then we should obtain the equilibrium Green's function for the final Hamiltonian, which we know already is 1 over z minus epsilon f. In an exactly analogous fashion, if t1 is less than 0 and t2 is less than 0, then we have an equilibrium Green's function for the initial Hamiltonian. G lesser of t and tau takes this form. Performing the Laplace transformation to the complex variable z from tau, we obtain g lesser of t and z. And then finally, just as before, we can obtain the retarded Green's function. This again takes exactly the form we expected, with 1 over z minus epsilon I now, with epsilon I being the level energy for the initial Hamiltonian. Much more interesting is the case when t1 is greater than 0 and t2 is less than 0, in which case we can define a lesser Green's function of our two times, t1 and t2, which we worked out earlier as this thing. Let's now convert this to t and tau. We can write g lesser of t and tau as I e to the I t into the difference between epsilon I and epsilon f minus a half tau of the sum of epsilon I plus epsilon f. When we perform the Laplace transformation of this, we obtain g lesser of t and z in the following form. The spectral function a of t and omega therefore takes this rather unusual form. We see that we have a delta function exactly at the average position of epsilon I and epsilon f, but that the amplitude of this has this oscillatory form in time. Then we also get this piece corresponding to the real part of the retarded Green's function times the sine of t, epsilon I minus epsilon f, and this is finite whenever we're not exactly at the pole position, omega equals a half of epsilon I plus epsilon f. You'll also notice that this spectral function actually can be negative. This is not a feature of equilibrium spectral functions, but it's something that can happen out of equilibrium due to these quantum quenches. So this was a simple example of a time-dependent Hamiltonian and time-dependent Green's functions that arise for such systems. In this particular case, we considered the 0 temperature quantum quench case, which is one of the simplest. It quickly gets more complicated with more complicated systems, but the basic ideas are the same. The final topic of today's lecture is how we calculate Green's functions for many particle systems. This is actually a big topic that will be developed further in the future lectures. However, today I just want to touch on a simple example of the quantum gas. So far, we just considered a single quantum orbital. In fact, now we're going to go back to the time-independent case, but we're going to add more orbitals. A quantum gas is one that is written in this so-called diagonal representation. We have a bunch of quantum orbitals, but they don't talk to each other, and all of the electrons in this system are independent. This is a quadratic Hamiltonian, meaning that we just have pairs of these fermionic operators, and there are no electronic interactions in the system. Furthermore, each of these orbitals is decoupled from all of the others. The important simplification in the case of a quantum gas is that the exact many-particle eigenstates of this Hamiltonian are product states in the occupation basis of each orbital. We can write an exact eigenstate of the system in this ket notation involving the orbital occupation for site number 1, 2, 3, and so on, and we can express this simply as the direct product of these complex vector spaces for orbital 1, orbital 2, orbital 3, and so on, where n1, n2, and n3 are the occupation numbers for those orbitals. This is an exact eigenstate of the Hamiltonian because if we apply h hat to this ket, we get the ket back again, multiplied by some scalar quantity, that's the energy in this case, of course, which is simply the sum over the orbital occupation for a given site times the site energy, and we sum over all sites. These nks being summed over here are not operators, they're simply the quantum numbers corresponding to the orbital occupation in this ket. So let's now have a look at the corresponding Green's functions for this system. I can define a lesser Green's function, for example, for orbital number j. I will label this g lesser with the subscripts jj. Since the Hamiltonian is time independent, I know that this will be a Green's function of a single time variable t. I express this as I times the thermal expectation value of the operator cj dagger multiplied by cj evaluated at time t, and j here labels the orbital. This is therefore the local Green's function for orbital j. Using the usual definition of the thermal expectation value in terms of statistical mechanics, and also the Heisenberg representation of the operator evolved forwards in time to a time t, we obtain the following. Z here is, as usual, the full partition function. These ket x's here are exact eigenstates, which are obviously going to be of this product state form that I wrote out earlier. Ex is the eigenenergy, which is this object. And inside here we have this bunch of operators. We have the creation and annihilation operators for site j, but we also have these time evolution operators. Note here that we're summing over all possible eigenstates of our many-particle system. The important point, however, is that this Cj operator and this Cj dagger operator only act on site j, and they commute with operators for all the other orbitals in the system. That means that even though the eigenstate denoted ket x here involves all of the orbitals, 1, 2, 3, and so on, these operators only act on the jth orbital. Indeed, given that we have a ket x here and a bra x on this side, the only thing that's changing by this string of operators is what's happening on the jth orbital. Everything else remains unchanged. Because of the product state structure of the eigenstates, one can then simply show that the lesser Green's function for orbital j is equal to I e to the minus I e j t times the Fermi function evaluated at epsilon j. The form of this Green's function equation is exactly the same as that which we obtained for a single quantum orbital. So we see that for the quantum gas, where we have a bunch of non-interacting quantum orbitals that don't talk to each other, the Green's function for each of those orbitals is as if we have just a single orbital. And the same results also hold for the greater and retarded Green's functions. I will leave it as an exercise for you to confirm these results. Indeed, when we perform the Laplace transformation to our complex variable z, we find that the retarded local Green's function for orbital j is simply 1 over z minus epsilon j, as you might have expected. Of course, in our many-particle system, we can also define non-local Green's functions. For example, consider g lesser ij of t, where I and j now refer to different orbitals. This would be defined, as before, as I times the thermal expectation value of these operators. We have c dagger for orbital I and c of t for orbital j. We can write this out in the same way as before, using our definition of the time evolution of the operator and our expression for the thermal expectation value from statistical mechanics. Remember that these kets here are the many-particle eigenstates, and we're summing over all of those. We can now immediately see that this entire matrix element here is proportional to the Kronecker delta, delta ij. That means that this object is precisely equal to 0 if I and j are not the same. This can be understood by imagining the action of a Cj annihilation operator for site j upon some arbitrary ket, which I've labelled here in the occupation basis. We see that this will give exactly 0 if nj is equal to 0. That's because we're trying to annihilate something in orbital j, and if there's nothing there, then this will give 0. On the other hand, if nj is equal to 1, then I can annihilate the electron in that orbital, and I would obtain this ket. Let's now consider feeding this ket back in and operating on it with Ci dagger, the creation operator for orbital I. This will again annihilate the ket if Ni this time is equal to 1. That's because of the Pauli principle. I cannot create an electron in the ith orbital if it's already occupied. On the other hand, if Ni is equal to 0, then I will get this ket. So the only non-zero contribution when I act with Ci dagger Cj is a ket where there are no electrons in the ith orbital and one electron in the jth orbital. When I act with this operator, I then end up with a state with one electron in the ith orbital and no electrons in the jth orbital. Note also that the occupation numbers of all of the other orbitals are exactly the same on the left-hand side and on the right-hand side. The Ci dagger Cj operator doesn't affect the number of electrons in all of the other orbitals. Now, the important thing is that the matrix elements appearing in our Green's functions involve the same state, ket x, and bra x. It's the same x in both cases. X, of course, is just shorthand notation for all of these occupation numbers here. And now you can see that if I were to pre-multiply this equation by the bra of this state, then I obtain this matrix element, and this is equal to 0, because on the right-hand side, I would have the bracket of this state with this state, and these are orthogonal. So this shows that if the operators I and j are not the same, then that means that this matrix element will be equal to 0. Fundamentally, this is because the Hamiltonian conserves the individual particle numbers of the different orbitals, and this operator, Ci dagger Cj, is changing the orbital occupation of the two sites I and j. In our Green's functions, we have additionally these time evolution operators, but you can easily put those in yourself and convince yourself that this argument goes through. And what this shows us in the end is that our Green's functions for the non-interacting electron gas, where the orbitals are totally decoupled from each other, are exactly local. This means that G lesser ij of time t is proportional to the Kronecker delta ij. If I is equal to j, then we get the familiar result that we derived previously for a single orbital. If I is not equal to j, then the Green's function vanishes. And this holds also for the greater functions and the retarded functions, as well as their Fourier transformed counterparts. Of course, this locality condition on the Green's functions is a peculiar feature of the non-interacting electron gas, where each orbital is decoupled from the others. We'll see in the coming lectures how in realistic models of real materials and molecules, for example, we don't have eigenstates which conserve the occupation number of each orbital. In that case, we can have finite non-local Green's functions, which correspond to the electron propagation from one site to the other. We'll be discussing those in detail in the coming lectures.